All right, so this is going to be module number 11. It's about formal notions of complexity. Recall that module number 10 was talking about orders of growth, and now we're going to formalize that into computational complexity, and similar notions can be used for storage complexity, memory complexity, and so on. So complexity earlier was a word for information complexity. How many bits, how much information, how much probabilistic uncertainty does the data have? And now complexity has the notion of the rate of growth of size. So we have different types of computational complexity, and it's a formal classification of functions based on the rate of asymptotic growth. And the details will be coming up, but let me give you a preview. A function f of n, it perhaps grows with n or maybe diminishes with n, and we say that it's capital theta of g of n. That means that g of n provides a tight asymptotic bound for the rate of growth of f of n. Or in other words, f of n and g of n, they grow together. We say that f of n is big O of g of n, meaning that we now have an upper bound for f of n. F of n grows no larger, no faster than g of n. Alternately, a lower bound is omega of g of n. That means that f of n grows at least as fast as g of n. And finally, our last formal definition, again, these are all going to follow formally. F of n is small o of g of n if f of n vanishes relative to g of n. So let's begin with the first one, asymptotically tight growth. N is going to be the size of the input. It's going to be a natural number, positive typically. F of n and g of n are going to be positive functions. And when we're talking about resource consumption tends to be positive, right? And now the formal definition is as follows. Theta of g of n is a class of functions, okay? So we're talking about, intuitively, all the functions that grow asymptotically as quickly as g of n. And formally, it's the class of functions f of n such that f of n is upper and lower bounded by c1 g of n and c2 g of n. G of n, recall, is positive. The constant c1 is positive, and therefore the product is positive. F of n is greater than or equal to c1 g of n, and it's also less than or equal to c2 g of n. C1 and C2 are constants, they're positive. And this rule must apply the inequality for all n that are sufficiently large. So n sub 0 is another positive constant. So bottom line, f of n is theta of g of n. That implies that f of n is a subset in the set of functions. F of n is in the class of functions that grow asymptotically just as fast as g of n. So you can imagine that this would be n, horizontal axis, vertical axis. We would have f of n and g of n. So let's say that g of n is this thing. And let's say that c1 times g is this thing, and c2 times g is this thing. And as long as starting from some n0, the function f is sandwiched between c1 and c2 times g, we're good. It could be that for smaller values, n less than n0 was bigger or less, doesn't matter. We're talking about asymptotes. Asymptotically, for values of n larger than n0, it works. And the main idea here is that we can ignore the lower order terms. So if we have cubic terms and quadratic terms, and only the highest order term matters. The others asymptotically go away. And let's see an example. So let's show formally that n squared minus 3n is theta of n squared. So before showing this formally, let's interpret this. We're trying to say that there's this class of functions, theta of n squared. These are the class of functions that asymptotically, for large n, they grow similar to n squared. And we're saying that subtracting 3n doesn't really matter here. And n squared minus 3n asymptotically behaves like theta n squared. So let's talk through this step by step. We need to find constants C1, C2, and N0 such that we'll be able to show that C1 times G of n is less than or equal to F of n is less than or equal to C2 times G of n. Okay, so now that we understand what we need to show, let's substitute. So specifically, we want to show that C1 times, well, G of n is n squared, is less than or equal to, so F squared is equal to n squared minus 3n. And we want to show that it's less than or equal to C2 times n squared. Let's now divide everything by n squared. So we want to show C1, C2, N0 such that ST C1 times n squared divided by n squared is C1 is less than or equal to n squared divided by n squared is 1. 3n divided by n squared is, so we're subtracting 3 over n. And we want to show that it's less than or equal to C2. So now let's think about it. N is going to be, provided that n is greater than 1, 3 over n is well defined. And in this case, 1 minus 3 over n is less than or equal to 1. And we can choose that C2 is equal to 1. What about the other part of the equation? So let's take, so C1 is less than half, right? So C1 is less, or I'm sorry, C1 is less than C2, which is equal to 1. We'll take, and C1 is greater than 0, we'll take such a C1 and fix N0 accordingly. As an example, let's take C1 equals half, okay? Just halfway between 0 and 1. So we want that 1 minus 3 over n is greater than or equal to half for n large enough. Now let's think about it. If n is 10 or more, 1 minus 3 over n is greater than or equal to 1 minus 3 over 10, which is equal to 0.7. Therefore, n0 equals 10 is good enough. Now, some of you may be thinking, oh, we can do better than n0 equals 10. And in fact, n0 equals 6 is better. Why? Because for 6, n0 equals 6, we have that 1 minus 3 over n0 is 1 minus 3 over 6, which is equal to half. So that would be a tight function, but 10 is good enough. All right, so now let's finalize what we have here. The bottom line is that we have C1 equals half, C2 equals 1, N0 equals 10. And recall, I was saying that 10 is good enough for the first inequality between C1 times G of n and F of n. What about the second inequality between F of n and C2 G of n? So we said that that's always correct. All right, so when n is greater than 0, as I wrote here, it's always correct. And therefore, n0 equals 10 applies for both the first and the second inequalities. So we have C1 equals half, C2 equals 1, N0 equals 1, such that C1 times G of N is less than or equal to F of N, which is less than or equal to C2 times G of N for all N greater than or equal to N0. We're done. Now, graphically, we can think of things as follows. This will be N, and we have G of N is N squared. Okay, so I tried to give it a parabolic shape. And G of N is equal to C2 times G of N, because C2 is equal to 1. And recall that C1 times G of N, C1 is half, and because of that we have half the function. And what we said that starting from the location 6, the new function is like, let's do that in red for emphasis. The new function is in the range. Okay. Let's move on. So we've talked about theta of n. Formally, it's tight asymptotic growth. Let's talk about the other formal definitions. Big O of g of n. This is the class of functions that is upper bounded by c times g of n. It's not lower bounded by something that's proportional to g of n. It's lower bounded by 0, except that the functions f and g are both positive functions. So bottom line, it's pronounced big O, and there's only an upper bound. Omega. So a function f of n is in the class of functions that's defined as omega of g of n if f of n is lower bounded by c times g of n. C times g of n, c is a positive constant, g of n is the other function. So you see that both the O definition and the omega definition, they used a single constant, which we were denoting by c, whereas earlier we had two constants, c1 and c2. So omega and O, when they both apply, we have theta. O is, or big O, is an asymptotic upper bound. We're upper bounding f by g. Omega means that we're lower bounding. F grows at least as quickly as g asymptotically, and theta means both, so it's a tight asymptotic bound. What about a small function? So f might be growing, but maybe f grows asymptotically much less than g. So we say that f of n is small o or little o of g of n if the limit of the ratio between f of n and g of n goes to 0. Some intuition. Let's consider the set of all functions. We have the set big O of g of n. These are functions growing no faster than g of n. We have the set omega of g of n, functions that grow at least as fast as g of n. And again, theta means that the function is both growing at least as fast and no faster than. It's growing exactly as fast asymptotically as f of n. So that'll be it for module number 11, and we'll continue next time.